or make it available in NTU Learn after the lecture is finished. Also, the lecture notes, this week I will make it available after the lecture, but from now on in the future, as Charlie suggested, I will make it available in NTU Learn in the weekend before the lecture. Okay, so for next Tuesday's summary lecture, I will put up the lecture note in this weekend and so on. Okay, so for your online lecture, just make sure that you mute your microphone unless you wish to speak. Of course, when you want to speak, ask questions or make comments, you're welcome to unmute yourself. But if you forget to mute it and then you do something else, then all the noise will come in. You can either unmute yourself to ask questions, or you can also type your questions or comments in the chat box, which I will check time to time. So we continue on with the second part of the course. So just a quick recap on what we did last week. So we looked at electric force. So when you have two charges, whether they are of the same charge or opposite charge, there will be a force acting between them. So if they are of the same charge, then there will be a force acting against each other, like in the picture here. If they are of the opposite charge, then there will be a force attracting them. And then that amount of the force will depend on the size of the charge, which is measured in coulombs, and also distance between them. So if they are closer together, there will be a stronger force. And if they are far further apart, then there will be a smaller force. Okay, and the force itself, the magnitude of the force itself is given by this Coulomb's law. And this is the equation where Ke is a constant. And from this electric force, we can also compute electric field, or which is defined as a force acting on a small test charge and divided by the size of the charge, where the size of that charge goes to 0 in the limit of it going to 0. Okay. So basically, electric field is just electric field. You can have electric field just with one charge, whereas with a force, you need to have at least two charges to have the force. But with the electric field, you can have electric field with just one charge. So that electric field for one charge would be given by this equation. So it depends on the size of the charge, which is measured in coulomb, and then how far away you are from that charge determines how strong the electric field is. So closer to the charge, it will be stronger. Further away from the charge, it will be weaker. And if you wish to calculate electric field caused by multiple charges or a group of point charges, then you would have to take a vector sum of individual contributions. Okay, so in this case, you have Q1, you have Q2, you have Q3. You calculate the electric field at this point P, if you wish to. So if you wish to calculate the electric field at this point P due to all of these three charges, then you compute the contribution from Q1 and draw that vector. Contribution from Q2, draw that vector as E2, and then E3 due to Q3, and then you do a vector sum of the three, and then you get finally the total electric field acting on P. Okay, and that's for group of point charges. Of course, if you have a continuous charge distribution, you actually applying the same idea. But because we don't have a discrete set of charges, but we have a continuous distribution, then we would have to consider them to be small, very infinitesimally small charges. And then we actually apply exactly the same analogy, but over an infinitely small charge over a fixed space in over the charge distribution itself. Okay, the charge distribution itself can be over a length, which we call a line charge distribution. It could be over a surface, which we call surface charge distribution, and it could also be over volume, which can be a volume charge distribution. And depending on whether you are you have a charge distributed over length or surface or volume, then the way you have to integrate would be different. So if it was over length, you just do a one-dimensional integration, whereas if it was over an area or surface, it would be a two-dimensional area surface integration. And it could be also volume integration if the charge distribution is over a volume. Okay. So the idea is exactly the same as that, but here in this case now you have infinitely small charge distribution, so you have to take an integral. And we also talked about electric fields, how you can draw electric fields to show the direction and magnitude of the electric field at certain point due to the presence of the charges. So we learned that the positive charge, the field lines will always start from positive charges, and they will end at negative charge. So this is called source, and this is called sink. We also know that the two lines, the electric field lines, will never cross, because you will always take the vector sum of the two vectors if they are at the same point, and then you need to take the vector sum, and that would be the resulting electric field at that point. So we will actually never have two lines crossing. Okay. So what these lines indicate is how, if I put a very small positive charge here, in which direction the charge will move, and how much the force it will how much force will act on it. Okay. So the strength of the electric fields at this location here will depend on how densely populated these arrows are. So you can kind of see that if I go further out here from this point here, the lines will spread out, and then I will have much less density of the electric field lines. That means the electric field will be much smaller at that point. Whereas around here, the density of these arrows are very high. That means the electric fields are high. So any questions on the part that we've done last week? Okay. So if not, then I will move to this week's content, which is on Gauss's law. Okay. So before we discuss what Gauss's law is, we need to understand the concept of electric flux. Okay. So flux is so just before, when we talked about electric field and electric field lines, we discussed that the electric field is kind of a density, how densely packed these electric field lines are, right? And electric flux, on the other hand, is you multiply the electric field and the surface area, a certain surface area, to then that will give us how many total number of electric field lines will be going through that particular given surface area. So in this picture, these orange lines are the electric field lines, and they represent the field strength. So the density of these lines represent the strength of the field. And then if I put an area, a piece of paper, which is perpendicular, or it's 90 degrees to the direction of the electric field, like that, like in the picture. So you have to see this in the three-dimensional. You have to imagine this is three dimension. And then the total number of lines that are passing through this piece of paper will be the flux. Okay, so that's pretty simple. So here and you can see that electric field, as we've seen before, is measured in newtons per coulomb, right? Because this is how much force would be acting on a particle of unit charge. Okay, so it is measured in newtons per coulomb, but because we are multiplying it by area, the unit of the flux will be given in newtons per newtons meter squared. That's for coming from the area. Area, the surface area, and then per coulomb there. Or newtons per coulomb is also equivalent to volts per meter, but now multiply meter squared to that, and then we get volts meter. So these two are equivalent, and then these two represent the unit for SI unit, let's say, for the electric flux. Here we use the capital phi. Okay. Okay. So electric field E, as we discussed, measures the density of the electric field lines passing through this surface. How many lines per unit area would be passing through there? Then, when you multiply it by the area, then we can kind of see that that the flux measures the total number of electric field lines. Right? Okay. So let me mute. All right. Okay. Then this is considering that the lines passing through and the area, they are 90 degrees to each other. So what if they are not at 90 degrees to each other at an angle, right? So that's the case that we will be looking at next. So this purple area, purple highlighted area, is at an angle. It's not 90 degrees, or it's not 90 degrees to the electric field. Okay, it is like at an angle like that. Then the flux should have exactly the same meaning. In fact, if the what flux should mean is that it should still calculate the total number of field lines that is passing through this area. Then how do you calculate that when the surface area is at an angle? Is that you actually need to consider this green box, green rectangle, which is a projection of this purple highlighted rectangle that is at a 90 degrees to this electric field. Okay, so we've discussed, I think we've discussed last time, that area can also have a vector. Area can also be represented as a vector, right? Surface area can be represented as a vector, where the size of the magnitude of the vector is equal to the area itself, the size of the area, and the direction is always normal to the surface, right? So in which case, if the area vector and electric field are pointing to the same direction, then we know that the flux is given by simply multiplying the electric field with the area, the size of the area. But as the area vector moves away from the direction of the electric field, it will reduce because the number of lines passing through, as you change the angle of the surface, is going to reduce. And at what point would it become zero? It would become zero if the surface itself is in the same direction as the electric field, or the surface vector is 90 degrees to the electric field, right? So you can imagine that I increase this theta to larger and larger, and then make this theta 90 degrees. At that point, this area vector would be 90 degrees to the electric field, and at that point, the flux through this purple lighted area is going to be zero, because you can also see that the line passing through this area is going to be zero at that point, right? So in order to calculate the flux, and then we have to calculate this projection area, which is highlighted in green, and that is calculated by taking the cosine theta, where the theta is the angle between the area that the surface vector that is normal to the normal surface vector and the direction of the electric field. Take that theta, and then you take cosine of it, and that will give you this projected area. And you multiply that with E to get phi. In other words, it will be given by this equation here. Okay, and that using dot product, we can express it this way. So having calculate dot products of two vectors means you are looking at the projection of one in the same direction to the other one, and then you take the magnitude of that, and so dot product of two vectors will give you a scalar answer. So this is also called scalar product as well. Okay. So this is for a surface that is at an angle to electric field. Actually, this we can work out that if theta is to be 90 degrees, we just discussed that when theta is 90 degrees, there's going to be no lines passing through that area, because area is like now the surface area is pointing up, and then the electric fields are pointing in this horizontal direction in this case. And then you can see that there's going to be no lines passing through that area. And that's also represented in this equation here, because in that case, the theta is going to be 90 and cosine of 90 is 0. So that the whole thing is going to give us 0, right? And the maximum is going to be when this theta is 0. When theta is 0, then we will have the surface at 90 degrees normal to the direction of the electric field. And then that is going to give us cosine of 0 is 1. So that's going to give us the maximum, E times A at that point. So this is for a flat surface, whether it's at an angle to electric field or normal to electric field. We can also calculate a similar thing for non-flat surface or even for non-uniform field. But in this case, like how we did it with a charge distribution, we need to consider infinitesimally small surface area and how electric field is passing through that particular area, and calculate the dot product between the electric field passing through that small area and the small area surface vector passing through there. And then we need to integrate over the entire surface, the non-uniform surface, okay, non-flat surface or non-uniform field surface. So so this is the basic idea of calculus, or basic idea of integration, is to take very small parts, infinitesimally small parts, and then add them all together to calculate the whole thing. But that, of course, has to be a vector. So you need to consider the vector nature of all these infinitesimally small surface area, as well as the electric field passing through there. But the entire thing, in fact, is going to be a scalar value. It's going to be a single. It's not. It doesn't have any. So flux is a scalar quantity. It's not a vector quantity. So I'm going to take an example. Yeah. So let's look at this example. We have a hemispherical surface. So what is a hemispherical surface? It's like a half sphere. Okay. It's like half of a sphere. You cut it. And then, of course, there's going to be a part that is half sphere, and then there's going to be a part where it is flat surface. I mean, you can have a real surface there, or it can just be empty there. Okay, doesn't really matter in this case. Anyway, a hemisphere surface, which is half of a spherical surface of radius r is equal to 2 meters, is in a uniform electric field of magnitude. So we have an electric field coming down in this direction at 20 volts per meter, or 20 newtons per coulomb. And this is normal. This direction of the field is normal to the surface that is flat on the hemisphere surface, which is this yellow highlighted part. And then the question is asking, what is the magnitude of the electric flux through the hemisphere surface? So we need to calculate what is the flux through this blue highlighted or blue colored surface. Okay. So how would you do that? Like if you try to calculate the electric field going through just all over there, that's actually going to be quite difficult. But you can kind of see that whatever the field lines going into this yellow, because this is at 90 degrees to this yellow flat surface, whatever the lines going through that yellow is going to be exiting through this blue surface, right? So we can make use of that. We can make use of that, and then say that we calculate the flux that is going through this yellow highlighted circle, which is going to be pretty simple. You just calculate the area of the circle, which is going to be pi r squared, and then you multiply it by the electric field, because that is at a normal angle, at a 90 degrees to the surface, then that exact number is going to be the flux that is going through the blue spherical surface. And then by that way, you can calculate the flux through the blue surface with a very simple calculation like this. Okay. So, any questions up to this point? So it is very important to understand the difference between electric field and the flux, electric flux. Okay. So field is the density of the electric field lines. Think of it like that. And electric flux is the total number of electric field lines that is going through that particular area which you are trying to calculate. That's the most important concept in this this part. Yes, so the signs of the flux, how to determine that, we will look at that very soon. Actually, that's the very next topic that we're going to talk about. Thank you for the question. Just adding another comment is that the sign of the flux is going to depend on whether the electric field, the direction of the electric field and direction of the surface vector, right? So if they are in the same direction, if they are pointing to the same direction, that will be positive. If they are pointing in the opposite direction, that will be negative, because if they are pointing in the opposite direction, the theta is going to be 180 degrees, and then cosine of 180 is going to be -1. But then the question is, which way is A pointing to? Because in this case, if we look at this purple highlighted rectangle, A can be pointing that way. Also, another possibility is A is pointing the other way, right? And you need to determine at one point what is going to be the positive A, whether it's this one or that one. And that one we will be discussing. Okay, so this is what I'm talking about. So now we're going to talk about electric flux going through a closed surface. So what is a closed surface? Closed surface is a surface that fully encloses a volume. So you have let's say you have a soccer ball, right? A soccer ball, the surface of the soccer ball completely encloses a sphere inside, right? A volume, a spherical volume inside. So that's, we can consider as a closed surface. But if I just have, let's say, this piece of paper, I just have this piece of paper, this is a surface. That's a two-dimensional surface, but it doesn't close anything. So it is not a closed surface. So you need to be able to distinguish between a closed surface and a not closed surface. Okay, so if I wrap this around and then I close here and I close there, then that's going to be a closed surface, right? So this is often also called Gaussian surface. Okay, so these kind of closed surface, which fully encloses a volume, is also called a Gaussian surface, and we will see why it is called Gaussian surface in a minute. And with this kind of closed surface, we can have direction in the surface vector. Okay, so in this case here, there's no really a rule on whether A should be this one, pointing upward like that, or whether A should be pointing downwards in this direction. There's no real rule about that, but With a closed surface, we can come up with a rule. And the convention is that the surface area vector A will always be pointing out of the closed surface. Okay, so let's talk about this is a closed surface. It's not a cube, but it's a block. Okay, it's a rectangular block, let's say. So with this rectangular block, on this surface here, on this left-hand side surface, the direction of that surface vector is going to be this way, this dashed line arrow, that one. Okay. Whereas with this one, it's going to be A is now pointing that way. Okay. So if the electric field is going in this direction through this closed volume or closed surface, then we can kind of see that on this area, the A and E are in the same direction. The area vector and electric field are in the same direction. Whereas this one, A is because A has to with a closed surface, A has to be pointing out of the closed surface. This is going to be in the opposite direction. E and A are now in the opposite direction. Okay. What about this one? This top part of this rectangular block. Which way would the A be pointing to? It will be pointing upward, like that. Okay, it will be pointing upward. And then the one down there is going to be pointing downward, because that's where that is what it means by pointing out of the closed surface. And then the one that is in front of us is going to be pointing towards us, towards the out of the screen. Whereas this one at the back, this surface at the back is going to be pointing into the screen. Okay. So I hope this is very clear to you. And then in this case, then when we calculate the electric flux through all of these surfaces, okay, if we calculate the electric flux through all of these surfaces, we can kind of see this one. We can compute E times the area, because it's 90 it's perpendicular to each other, so we can simply do a arithmetic multiplication between the two numbers. And are we going to get a negative number or positive number in this case? Because electric field and A vectors are pointing in the opposite direction, we're going to get a negative number. And we can also kind of see it from the theta being 180 degrees, because these are now in the opposite direction. Theta is going to be 180, and when you substitute 180 here, cosine of 180 is -1, so we get a negative flux. So that whole part is going to be a negative flux. Okay. How about this one? This one, now A and E are in the same direction, so that means we're going to get positive, and theta is 0. This is 1. And we're going to get positive flux. So the flux through this surface is going to be positive flux. Okay. Are there any flux going through this surface? The top surface? No, because there's not going to be any lines, going through this area, because you can imagine this is infinitely thin. And then, even if you have very densely packed lines, no lines going to go through this area, of course, because that's it's a flat area there. And same with the one at the bottom there. That is because this angle, which is the what is this? This the area, the surface vector pointing upward. That's at a 90 degrees to this field. So when you put cosine of 90, that's going to give us 0. Okay. Same with the bottom one there. It's going to be pointing downwards, and then that angle, perhaps now we can call it 270 degrees or something, or 90 degrees again. Then that's again going to be 0. And then also these two surfaces that are in front of us and not in front of us, but at the front and at the back, they are also 0, because there's going to be no line going through those surfaces. So there's only these two surfaces where you have flux, and one is negative, and the other one is positive. Okay. All right. So we'll take a look at an example of electric flux going through a closed surface. So let's look at this example. We have two concentric spherical surfaces. So concentric spherical surfaces mean they share two spheres, share the same center. They share the same center, but one has smaller radius. The inner sphere has a smaller radius, and outer sphere has a bigger radius. Okay, but they share the same center, which is I've just drawn here. Of radius r and 2r respectively, surround a positive point charge q. So there's a point charge q in the middle, right in the middle. Find the electric flux through the two surfaces. Okay. So when we have a sphere, and then in the middle, right in the middle, we have a charge. Are we going to have the same electric field throughout the entire surface of the sphere? Should we have the same electric field throughout the entire surface of the sphere? The answer is yes, right? Because if we remember, I'll come back. If we remember, the electric field is a function of the size of the charge, Q, which is fixed in the middle. And then it depends on what? It depends on the distance. And if we have a sphere and you have a charge in the middle, then on the surface of the sphere, the distance from the surface to the charge, any distance from anywhere on the surface and to the charge is going to be always the same, right? That means electric field on the surface of this sphere is going to be all the same. Okay. So, and that is going to be given by what? So what this means is the electric field at distance r from the center of the sphere, and distance r is going to be the surface of that sphere, is given by the Coulomb's constant times the charge in the middle, and then divided by the radius squared of that little sphere, right? Inner sphere. So we know what the electric field is going to be, and you remember how we draw electric field of a point charge is going to be when we have a positive point charge, it's going to be directed radially outwards, right? And it will be a three-dimensional radially outwards like that. Okay, so you can kind of see that at each little elements of the surface, each little surface element on the surface of this inner sphere is always going to be 90 degrees. The surface area is always going to be the 90 degrees to the direction of the electric field. Okay, so that means we can actually do a simple multiplication of this ER, which is the electric field on the surface of the sphere, with the area of the surface area of the entire sphere, okay, which is given by 4 pi r squared. Okay, which is given by 4 pi r squared. Okay, so then the flux going through the entire small sphere is going to be ER times 4 pi r squared. And knowing that this ER is this, then we can simplify and we get what? We get Q divided by epsilon 0. Everything just cancels out, and then we get Q divided by epsilon 0. Why are we getting? Where did the KE go? Where did the KE and where did the 4 pi go? If you remember, KE, which is the Coulomb's constant, is given by 1 over 4 pi epsilon 0, right? That was from previous summary lecture last week. So KE is 1 over 4 pi epsilon 0. So putting that in, then it will cancel out 4 pi, and then you have epsilon 0 in the denominator, and you have Q in the numerator, like that. Okay. Now, let's calculate the electric field going through the outer sphere, which is a bigger one. And we can actually apply the same logic because it's, again, the charge is in the center of the larger sphere. So it's going to be Q divided by, in this case now, instead of R, because now the distance from here to the surface of the outer sphere is going to be 2R. You need to put 2R squared like that. Okay. So again, we apply the same logic. We know that the small surface area here will always be at 90 degrees to the direction of the electric field around there, just at that point. Okay. Then it's going to be a simple multiplication. The flux through the total surface of the outer sphere is going to be the surface area of the outer sphere, the simple multiplication of the electric field at that point, and the area of the outer sphere, the surface area of the outer sphere, which is given by, again, 4 pi r squared. It was r squared here, but now is 2r squared. And if you expand this out, we get that, and then we can cancel out of stuff out, and then we get to the same point, and we can express this as Q over epsilon 0. So you get a very interesting answer in this case, in this example, is that whether you have a small sphere inside or whether you have a larger sphere inside, the flux going through the small sphere or the large sphere, they are exactly the same in this case. Okay, why is it the case? Because with the outer sphere, the surface is further away. Its surface is further away from Q. So the electric field going through the outer sphere is going to be smaller, right? Because it is further away. But still, we somehow get the same flux. That is because what? That is because we have a larger area to cover with a bigger sphere, right? We are covering a larger area, so that compensates out the weaker electric field on the surface itself. And it exactly compensates out. And we'll see why, in fact. Okay. So this, the fact that we get exactly the same answer, and this answer doesn't depend on anything about this radius of the surface, brings us to the Gauss's law. Okay, so we'll look at Gauss's law. Okay. So what Gauss's law says is that the net electric flux through any closed surface is proportional to the net charge enclosed in the closed surface. Okay, what that means is this is, you can imagine this is a three-dimensional surface, and it's a Gaussian surface, meaning it's a totally closed surface. So you can imagine this is a potato. Okay, and now the potato skin is your Gaussian surface. Okay, just have potato skin there, Gaussian surface, and there are some charges inside your potato somewhere, and then there are also some charges outside your potato. But so because you have the charges, this will create some electric field around it, right? Electric field around it, and then that's going to so I have drawn in all these field lines that is coming out of the surface, but of course it could also be going in to the surface as well. I've just drawn roughly what's or this is just a schematic diagram, so it doesn't represent anything real, of course. But then what this says is that if I integrate and if I calculate the total flux, the total net flux, so it could be negative or positive. So if I calculate, if my net flux is negative, what does that mean? That means there are more arrows going into the surface, the closed surface, than those that are coming out of the surface. Because coming out of the surface, we defined it to be positive, and going into the surface, we defined it to be negative. So, right? So net electric flux being positive means it's going to be there are more lines coming out of the surface than lines going into the surface. And net flux negative means there are more lines going into the surface than coming out of the surface. So and what this says is that the net flux, whether it is positive or negative, depends on how how much charge is enclosed within this Gaussian surface. Okay, so if we calculate the flux through this Gaussian surface, so this what is this integral sign with a circle in the middle means a closed surface. Okay, we are doing an integration over a closed surface. If we do calculate a flux through an enclosed surface, then it's going to give us the total charge inside it, enclosed inside that surface, divided by epsilon 0. Okay. So in this case, I'm giving as an example, there are 3 charges, Q1, Q2, Q3, that are embedded in the potato, and Q4 and Q5 are outside of it. And it doesn't matter what Q4 and Q5 are, the total flux, that is the total net flux through this Gaussian surface, is just going to be given by Q1 plus Q2 plus Q3 divided by epsilon 0. Okay, and you can kind of understand why this is going to be the case. Why is this going to be the case? Is because if you remember, the electric field lines, they only begin at positive charges, and they only terminate or finish at negative charges, right? So if we have positive charges here, then okay, if we didn't have any charges, like for instance in this one, let's say we didn't have any charges here, then these lines going through, they will not stop anywhere inside this volume, right? And they have to come out of another part of this closed surface somehow. So if you don't have anything, whatever that goes into this closed surface has to come out somewhere else. And going in is negative and coming out is positive. So you add them all up and then we end up having 0. So the net flux, total net flux, is going to be 0 if we don't have anything inside here. Okay, let's assume we have a negative charge in here. That means the lines will go in, and some of these lines will terminate inside there, right? Some of these lines will terminate inside, but some they will not be terminated. But then when you add all the lines going into the surface and lines coming out of the surface, when you add them all together, then basically you will end up having those. You will be able to count the number of electric field lines that has terminated inside the box or inside this enclosed surface, which will be proportional to the net charge inside. So if you have net negative charge, then there will be lines that are that terminated inside this closed volume, and then there will be lines that pass through. But by understanding how many lines terminated there, we can calculate how much charge is inside there. Or if we know how much net charge is inside there, we can find out how many lines will terminate or will begin inside this enclosed surface. Okay. So coming back to this example, the reason that we have the same electric flux through the outer sphere surface and also the surface of the inner sphere, the reason that we have exactly the same flux, total flux through those two surfaces of very different size and at a different distance from R, the distance from Q, of course, is that because it encloses, those two spheres encloses the same amount of net charge inside. Okay. That's why we have the same flux. We have the same flux, and it is the charge enclosed inside divided by epsilon 0. Charge enclosed inside the yellow sphere is Q, and charge enclosed inside the blue sphere is again Q. So we will get the same answer there. Okay. So any questions up to this point? Okay. All right. So if no questions, I will continue. So we will look at, I'll take a sip of water. So let's look at how we can apply the Gauss's law to charged insulators. So insulator means what? So in these examples, we'll be considering insulators as well as conductors. Okay. So insulators are where the charges cannot move and they are fixed in that position. So when we say there is a charge distribution in an insulator, the charge distribution never changes. It just stays there all the time. Okay. Whereas with a conductor, the charges will freely move. So they will move in a direction where it creates it ends up having zero electric field inside the conductor, which I think we discussed last time. But that also will appear later on. Okay, but for now, let's look at the insulator. So we have a uniformly charged insulating sphere. So it's a sphere. So it is like a soccer ball. And the charge is uniformly distributed over the entire volume of your soccer ball. Okay. So we have uniformly charged insulating sphere, field outside the sphere. So we want to calculate what the field is going to be outside the sphere, not inside the sphere, outside the sphere. So how do we do that? We can create a Gaussian sphere. So remember, in this, when we are defining it, I said it doesn't have to be a sphere, or it doesn't have to be a cube. It can be any closed surface. But now we have to be clever and we have to come up with a surface that is going to give us a nice symmetry and also something that is going to be easy for us to calculate. Okay. So I don't want you to put some I don't know, potato-shaped enclosed surface outside of this sphere, because that's going to give us a very difficult time calculating the electric fields. Come up with something that is very simple to calculate, like a sphere. Right? We know very much well about the sphere, and then also it's going to give us a very nice symmetry, because this is a uniformly distributed charge across the entire sphere. So that sounds like something that will have a spherical symmetry, spherical or rotational symmetry, right? So we can create a Gaussian sphere like that. And then what Gauss's law said is that the total electric flux, that is the total net flux through this Gaussian sphere, is going to be equal to the total charge enclosed within it, okay? And we know that the total charge, which is distributed over the entire the volume of this little ball, is going to be Q, because I've written it there. Okay, that's why it's going to be Q. And in order to calculate, and because this Q is all evenly distributed, we also know that the electric field at this Gaussian sphere, which shares the same center with this the charged ball, is going to be the same across the entire location on the surface. The electric field is all going to be the same, and the direction of the electric field also is going to be normal or perpendicular to the little elements of the surfaces. Okay, so I can write this two dot products. So that is the little element dA, surface element on the Gaussian sphere, and when I put this enclosed surface integral, means I need to calculate the surface area of the entire Gaussian sphere. So when I put this integral, then I can just simply calculate the area of the entire Gaussian sphere, and then do a simple multiplication of the electric field at that point, which is something that we're trying to find out. We don't know. Okay, but we can formulate it like that. And then we know that flux, which is going to be this, and of course, calculating the surface area of this Gaussian sphere at location R with the radius R is going to be 4 pi R squared. That's the surface area of a sphere. It's going to be Q divided by epsilon 0 from the Gauss's law. Okay, so using that, rearranging, we have E is equal to this, and then we know that 1 over 4 pi epsilon 0 is Coulomb's constant. So then we end up having this equation. So what does it say? It says if we are talking about the electric field outside this charged sphere, insulating sphere, outside the charged sphere, it is electric field at that point is going to be same as what? It's going to be same as having a point charge in the middle of the sphere. It is actually exactly the same. Okay? So that's what we get from this example here. Okay. We can also try to calculate how the field is going to be inside the sphere. Okay. So if we know that the sphere has uniform charge distribution, then we can calculate the uniform volume charge density rho, which is given in units of coulombs per volume or per meter cube. Okay, we can calculate that, and then we can draw in. So in order to calculate the field inside the sphere, we need to draw a Gaussian sphere inside the charged ball, right? Like that. Okay, like that. And then we need to we can come up with the charge that is enclosed in this Gaussian sphere, and that's going to be rho times 4 over 3 pi r cubed. So 4 over 3 pi r cubed is the volume of this Gaussian sphere. It's going to be the volume. So if you multiply volume by the charge density, volume charge density, then you get what? This is going to give us the total amount of charge that is enclosed inside this Gaussian sphere that is inside here, right? Inside the ball. So depending on how big our R is, the amount of charge that is enclosed in our Gaussian sphere is going to be different. When R is small, we have a very small volume. And of course, then the amount of charge enclosed within that small volume is going to be small. If we have large volume, or if we draw a large Gaussian sphere, then the amount of charge that is enclosed in the Gaussian sphere is going to be large. And when R becomes A, how much of the charge is going to be enclosed within our Gaussian sphere? We're going to have Q, right? Because when R becomes A, actually our Gaussian sphere is exactly the same as this the charged insulating sphere, and then the total charge enclosed within that insulating sphere was Q, so it's going to be Q if we do that. Okay. Anyway, so when we have when we draw the Gaussian sphere, we can calculate the charge enclosed within this Gaussian sphere using this equation. And what is this part? This part is the rho, because we know Q is the total charge within this spherical ball, the charged ball. And if we divide the Q by the volume, we're going to get the uniform volume charge density. So this is the uniform volume charge density. And then we multiply that by the volume of the Gaussian sphere. So you have to be able to clearly distinguish between the Gaussian sphere and this charged sphere. Okay, charged sphere has a fixed radius of A, whereas the Gaussian sphere is something that we can change. Is our imaginary sphere, which has the radius R. Okay, so that's going to give us our volume charge density, and this is going to give us the volume of the Gaussian sphere, which is going to give us, when you multiply the two together, which is going to give us the total charge enclosed within this Gaussian sphere, which is given by this equation. And then from this, we can calculate again the flux. The flux is going to be, again, because this is a uniform charge distribution in a spherical form, our E is always going to be the same. The electric field on the surface of the Gaussian sphere is always going to be the same. and it's also always going to be perpendicular to the little small patch of surface that is on the surface there, the little infinitesimally small patches there. And electric field direction is also going to always be perpendicular to each other. So we can do a simple multiplication like that. And then, of course, doing a surface integral of the sphere is going to be 4 pi r squared for the Gaussian sphere. And we can, from the Gaussian law, that's going to give us, multiplying these two is going to give us the charge enclosed divided by epsilon 0. And rearranging, substituting this in and then rearranging that, we get this equation. So what does this say? Now, when you are inside this electric field, inside this charged insulator ball, the electric field inside of it will depend on what? It will depend on the radius of where you are at in this charged sphere. Okay, so if you're in the middle, the R is going. If you are close to the center of the sphere, your R is going to be small, and then your electric field also is going to be small. But as you go further and further out, this is going to increase. Your electric field is going to increase. Okay. And when your R is A, what will happen? When your R is A, then your R is going to be when R is A, then actually the charge enclosed inside is going to be same as the total Q, okay, the total charge Q, and at that point it's going to be the electric field on the surface there of this uniformly charged insulating sphere. All right, so let's look at another example. This is another example of uniformly charged straight line. So we have this line where it is all where the line has all the charges uniformly embedded in the charge in the line, and we want to calculate the electric field going at some distance from this line. Okay, so at this point, let's say at this point. Okay, so how do we do that? Now, if this is very long, let's say infinitely long, then we know that any horizontal components would have to cancel out because each of these charges here is going to be creating the electric field radially outwards, but the field that is created this way by that point there is going to be cancelled out by another charge that is radiating out the electric field that way. So all that will survive is something that is directed outwards from the line itself. So this orange line is electric field. These are the electric field lines that will be created by this line of uniformly charged insulator, the uniformly charged straight line. Okay. Is that a clear picture to you? Okay. And in this case, how are we going to create a Gaussian sphere? Is we create a ring-shaped one like that. Okay, so we have or cylindrical shaped one like this. Okay, that's because you can kind of see that on this surface, which is a curved or cylindrical curved surface, it's always going to have that area, little area, infinitesimally small little area that is normal to the direction of the electric field, because electric field is always projected outwards from the line, from this charged line. So then it becomes very easy to calculate the flux. Are there any flux through these circles? No, because there are no horizontal components of the electric field. There are only the radial components that is coming out of in the radial direction from the line. So only the flux will only there will be only a non-zero flux through this surface. this surface which is wrapping around, let's say this straight line, right? So that means in order to calculate the flux, we just need to calculate the area that is surrounding here, which is going to be what? It's going to be the circumference of this circle, times L, because that's going to, when you straighten them up, when you flatten them up, it's going to be a rectangle. So it's going to be the length divided by width for the rectangle, where length is this L, and then the width of that rectangle is going to be what? It's going to be this circumference. So I can simply multiply 2 pi r L. So 2 pi r gives us this circumference of the circle, multiply that by L. And then if we multiply E, because E is always 90 degrees to this surface, we can simply do a simple multiplication like that. And then that's going to give us what? The charge enclosed within this cylinder. Charge enclosed within this cylinder divided by epsilon naught. And that comes from the Gauss's law, that one. Okay. And then so how do we calculate the Q enclosed within this cylinder? That's going to be given by the uniform charge density. Because this is a uniformly charged straight line, we can calculate lambda, which is the line charge density, the uniform line charge density. So if we we can calculate, we can say that the Q, the total charge enclosed inside here is going to be the charge the unit length charge density times the length of this line right there. Okay, so then we can substitute that in, and then we express our electric field in terms of how far you are from this line, as well as what is the line charge density of this line. Okay. The line charge density of this line. So let's take a look at this example. So it's an insulator example. So we have a material having a uniform volume charge density of 38 nanocoulombs. So this is going to be a volume charge density, 38 nanocoulombs per cubic meter. Fills a cube with a dimension of each side 8 centimeters. So we have a cube, and the charge is distributed uniformly inside this cube. What is the total electric field flux through the surface of this cube? So how do we calculate that? We know that the total flux is going to be equal to the total charge enclosed inside the cube divided by epsilon 0. So this is going to be the total charge enclosed inside the cube and divided by epsilon 0. And because we know the volume charge density and we can calculate the volume of that cube because we've already given the length of each side, which is 8 centimeters, then we can also calculate the flux this way. Okay, so that's pretty straightforward. Any questions on up to this point? So important part is how to figure out which Gaussian surface to use. In this case, it was fairly straightforward. We just use because the uniform volume charge is, it fills a cube, so it naturally gives us the fact that we should use a cubic. We should use a cube enclosed surface as a Gaussian surface. But depending on the problem, you need to come up with a clever way of forming a Gaussian surface. Okay. So let's look at. So that's all. That was all for insulators. Now we're going to look at conductors. So conductors will have slightly different. It has quite different behavior from insulators because charges can move freely. Okay, that means when conductor is at so-called electrostatic equilibrium, that means no charges are moving anymore. Okay, so equilibrium means like there was some movements of the charge, and then now charge don't move anymore because now everything is totally balanced. Okay, that is electrostatic equilibrium, and that means no net motion of charges. And when you have electrostatic equilibrium, your electric field inside the conductor is going to be zero. Everywhere inside the conductor is going to be zero. Okay, and if it's not zero, charges will move around because they are free to move. And then that means there's no longer electrostatic equilibrium. So once you reach the electrostatic equilibrium, the charges will not move anymore. And also the charges inside the conductor is going to be zero because if it's not, if the charge is inside the conductor, it will move to somewhere else such that it will move to somewhere else such that inside the conductor it's always going to be zero because we need to keep the electric field to be zero inside the conductor. So what happens on the conductor is any excess charge or any net charge on the conductor is going to they will all move to the surface, and they will all be distributed over the surface of the conductor. Okay, so inside the conductor it's always zero, but all the charges will accumulate on the surface of the conductor. Okay, and then for that reason, the electric field just outside the conductor is going to be normal to the surface, conductor surface. So if our conductor surface is flat like that, then our electric field, if we have any net charge inside the conductor, electric field is going to be pointing in the 90 degrees. And if we have some arbitrary shape, at each small sections of that, the electric field is going to be normal to that part there. So there are sometimes questions with conductors with a cavity inside. So what is cavity? Cavity is like an empty space. So you have this conductor, and then inside here there is some empty space there. Okay, and then in this question, this is also an example. We have no charge inside. We have no charge inside here, and then if we create a Gaussian surface inside here, there's not going to be any charge in here, right? Because there's no charge inside this cavity. So this one will contain zero enclosed charge. That means the flux through this Gaussian sphere inside this cavity is always going to be what? It's always going to be zero. Okay, so this green always must be zero everywhere. And likewise, inside here, are there any charges? Enclosed inside, are there any net charges enclosed here? We don't know. We don't know, right? We don't know. But what about the electric field? Electric field going across this part is always going to be zero because we are this Gaussian sphere is created inside where? Inside a conductor. And we already discussed that inside a conductor, electric field is always zero. Electric field is always zero. So that means here the electric field has to be zero all the time, okay, inside the conductor. So any Gaussian surface that is constructed within the conductor has to have zero flux because electric field is zero, okay? And that means there's going to be no net charge inside here because the field, the electric flux through this Gaussian surface, which is created inside the conductor, is zero. That means, according to the Gauss's law, that there are no any charge enclosed inside this outer sphere also. Okay, so if we had any excess charge in this conductor, they will all be residing in the outer surface, because remember, any net charge in a conductor will be residing on the surface, but here we have inner surface and outer surface. And in this case, when we don't have any charge inside the cavity here, there's not going to be any charge accumulating in the inner surface, but all the net charge is going to go to the outer surface and then they will be accumulated there. But the story changes if we do actually have net charge inside the cavity. Okay, so let's draw this Gaussian surface again. this Gaussian surface, inside the conductor. And as we know, the inside the conductor electric field is 0. That also means the flux through this Gaussian surface is going to be 0, because if you multiply 0 by the area, it's going to be 0. But the charge enclosed inside of it is not, charge enclosed here is not going to be 0, because we have some net positive charge inside the cavity. That means we have to have some charge accumulating on the inner surface of this conductor or around the cavity in order to create a net zero charge. Okay, because the Gaussian, because the flux through the Gaussian surface is 0, we must have 0 net charge enclosed inside of it. But because we have some charges inside the cavity, that also means we must have opposite charge that is accumulating inside the on the inner surface of this conductor. Okay, so that charge on the inner surface is going to have the same size as will be the same amount of charge that is enclosed in the cavity. So, any questions up to this point? So we're going to solve an example using this idea. So let's look at this example of the conductor. So we have a series of 3 uncharged conducting concentric shells. So what shells means? It's a spherical shell. It's a spherical shell, but it's empty inside. Okay, it's a spherical shell with that is empty inside. So we have concentric shell means we have 3 spherical shells that are sharing the same center point, and then surround a small central charge. So we have a charge Q inside here. Find the charge distributed on the outer surface of the third shell. So outer surface, this is the third shell outside, second shell, third shell. Outer surface is going to be out here. I've already put in the answer here, that is positive Q. But how we get to that answer, let's look at that, okay? We know that the total flux in a Gaussian sphere that is constructed inside a conductor is going to be 0. So if I create a Gaussian sphere inside this conductor, this little shell here, and that is enclosed, so it's going to be a spherical Gaussian surface, then I have to have I will have 0 net flux, right? Because electric field inside the conductor is 0, so I will have 0 flux. That means the net charge enclosed inside of that has to be 0. That means if this is Q, or if this is positive Q, then it has to draw in the inner surface of this sphere minus Q quantity of charges. Okay, it has to draw that much of charge accumulated on the inner surface of it. Okay, and because this spherical shell, this spherical shell is uncharged initially, if I was to draw negative Q charge on the inner surface, that must mean on the outer surface it must draw positive Q. The remaining charge must be positive Q there. Okay, because only by adding the charge drawn on the outer surface and inner surface, when I add them together, it has to be 0, because initially it was uncharged conducting concentric shells, right? And then we can apply the same logic. So I need to draw another Gaussian sphere just inside this conductor, and that flux has to be 0. That means the total charge enclosed must be also 0. So let's look at the total charge enclosed. This is Q. These two will add up to be 0. And then, because I need to make that into 0, that means also in the inner surface of this second shell, conducting shell, has to draw minus Q amount of charge on the inner accumulated on the inner surface. And then because this is uncharged one, I have plus Q on the outer surface accumulating on the second sphere. And then same logic applies on the third sphere, and then I have plus Q on the outer surface of this conducting shell, okay, concentric spherical shell. So that is how we can use Gauss's law to find out how much charge is going to be accumulating on each of these surfaces on the conductor. Okay, so with the conductor, the questions will often be asked how much charge is going to be drawn on the surface. There's never charge inside the surface. Inside the conductor, because the conductors will always move these free charges out to the surface, and they will all be accumulating on the surface. In the middle, inside the conductor itself, there is going to be zero charge. Okay. So anything that you'd like to clarify at this point? So if not, then I think we will summarize the summary lecture. So let's start second order summary. So we've talked about flux. So flux, as I said, is the total number of electric field lines passing through that particular area is flux. Okay. And we've discussed about the Gauss's law. So Gauss's law is defined as a total flux of an enclosed surface or closed surface. Total flux through a closed surface is equal to the total charge enclosed in the closed surface divided by the permittivity of free space, which is epsilon 0. This is just a constant, of course. And then we've discussed how we can apply the Gauss's law on charged insulators to calculate the field outside of this charged insulator as well as inside the charged insulator, and also how we can apply the Gauss's law on conductor. Remember that inside the conductor, electric field is always 0, and charge inside the conductor is always going to be 0. All the charges will only accumulate on the surfaces of the conductor. So with that, I will finish today's lecture. If you have questions, please remain, and you can welcome to ask me questions. If not, then I will see you next week. And I will remember to upload the lecture notes on either Saturday or Sunday. Okay. All right. Thank you very much. Have a nice week.